responsible for hosting this event today. Once again, I warmly welcome our guest speaker, Mr. Tharindu Suraj, who will be our guest speaker today. Today, we have all met here for knowledge exchange webinar on sensor integration and usage in UAV, hosted by the Aeronautical Division of SEDS SLTC. To begin, let me provide a brief overview of SEDS. SEDS stand for Students for the Exploration and Development of Space and is a non-profitable international organization that empowers young people to participate and make an impact in space exploration. SEDS helped students to develop their technical and leadership skills by providing opportunities to manage and participate in international projects, as well as to attend conferences, publish their work, and develop their professional networks in order to help students to become more effective in the present and future careers in industry, academy, government, and education. The Aeronautical Division of SEDS SLTC has organized the DRONERA Chapter 2 webinar on sensor integration and usage in UAVs in order to provide the aviation enthusiast committee get insight into this vastly complex field. Before we move on to today's event, I would like to invite Mr. 𝚂𝚗𝚗𝚘𝚗, Manager of the Aeronautical Division of SEDS SLTC, to deliver the welcome speech. Over to you, Mr. 𝚂𝚗𝚗.
Thank you, Pramod. Good evening, everyone. I'm 𝚂𝚗𝚗𝚗𝚗, Division Manager of the Aeronautical Division of SEDS SLTC. It is a great pleasure to welcome you all to the DRONERA Chapter 2 webinar organized by the Aeronautical Division of SEDS SLTC. First of all, I warmly welcome our honorable guest speaker, Engineer Mr. Tharindu Suraj Chathuranga, a specialist in UAV and drone technology and a degree holding electronic and telecommunication engineering at the University of Morocco. Founder and Chief Technology Officer in SRK Robotics and former research engineer at the University of Morocco. Also the academic head of Bionic B Academy. Once again, we warmly welcome you, sir, to today's webinar. I would also like to welcome all the lecturers and staff members present here today. I extend my welcome to the Executive Committee and all other members of SEDS SLTC. Finally, I welcome our wonderful participants present here today. We are very excited to have you all here participate in this one-day webinar and hope you will enjoy this event. Thank you.
Thank you very much, Mr. 𝚂𝚗𝚗. Okay, let me make a few important announcements before we commence. We kindly request our audience gathered here today to mute your microphones to avoid any disruptions due to the background noises. Q&A form will be given during the webinar and Q&A sessions will be held at the end of the webinar to clear up any confusion. What are we waiting for? Let's move on to the most remarkable part of our webinar. Once again, I would like to welcome our guest of honor and speaker. It's a great privilege to have you with us today, sir. Mr. Tharindu Suraj, I'd like to invite you to begin this session.
Right. Okay. Good evening, everyone. I'm Tharindu, and thank you for the great introduction. And as explained, today's topic will be the sensor integration and how are they being used inside unmanned aerial vehicles, so drones. Right. So I think you all have now aware of what UAV or a drone is. And most of you sometimes have experience in flying drones. But we need to understand what's happening inside the drone and what are the complex computational activities going inside the circuitries, and how can we become drone engineer, or how can we become a researcher in the relevant field by understanding these kind of use cases, and how we can integrate other types of sensors apart from the main sensors that are already existing in the current UAV systems. Right. So before we begin, this is my profile. I think you already explained that. So rather than the things that you mentioned, I worked as a research engineer at the research intern at the Australian National Science Agency. There I got hands-on experience on several UAV projects, and because of that, I got several research awards from all over the world, especially in USA and Australia. And I need to acknowledge something. Almost all the contents that I present here are extracted from the Bionic Bee Academy, where they teach advanced robotic systems and UAV technology. And I think they are the only academy which teaches these kind of technologies, because I haven't seen any kind of private or government universities teaches this kind of stuff. So again, almost all the things that I going through today are extracted from the course materials of this academy. Right, you can head to their website and their Facebook page to find out more details. Okay, so before we begin, we need to understand what are the basic angles of a UAV or a drone is. We mainly call these as oil angles, and there we can identify three main types: roll, pitch, and yaw. Roll means if this is the head or the front of the drone, then roll angle means you swing side by side. Then pitch means you move the nose up and downwards, and that's called the pitch. And then we have a third movement, yaw, which means you are not changing the horizontal or vertical angle. You just rotate at the horizontal plane, and that's called yaw. You need to properly understand these three angles, because when it comes to the drone industry, we usually use these three movements in order to identify any type of a movement or a maneuver that we perform. So you need to keep that in mind and understand all these three movements and what are the axes when it comes to the Cartesian coordinates, and that will eventually help you to understand how these sensors works in the next few slides. Before we talk about the types of sensors that we can see inside a drone, let's see a flying video of a drone, and I'll explain what's happening there after we watch this video. Here, what we can notice is drone is flying, and the main thing is you can notice it's quite stable. It's not going here and there. And now you can see the user is not controlling the drone using its remote controller. So what we can get from this video, what we can understand. The first thing is, if I play this video again, the first thing is the drone is holding a position without getting the commands from the user. That's the first thing. And we can see even the user is not giving any kind of a command to the drone. The drone is not figuring any kind of aggressive movements. Sometimes if you have a flaw on a drone, you know how hard it is to keep at one place, because you need to continuously control it, otherwise it will go somewhere and crash. But here, this drone hovering at one position even without getting the commands from the user. That's the first part. And obviously it is flying at a stabilized position. It's not going here and there. It's maintaining its level, which means its plane is at a horizontal plane or parallel to the ground. Then you can notice that its altitude or the height from the ground is almost a constant. It's not changing or it's not fluctuating. That's the second thing. Third thing is it's not moving in the horizontal plane, which means it's exactly holding its position at one place apart from the altitude. Altitude is moving in the vertical plane, and in the horizontal plane, it's not moving. Right. So what we can understand from this video, in order to fly or in order to hold a position, we need to maintain three things. The first one is we need to maintain the stability of the drone, or we need to maintain the drone parallel with the ground. That's the first thing. Then we need to maintain the altitude, or the height or the distance from the ground. That's the second thing. The third one is you need to keep the horizontal position at one place, which means the drone needs to be hover at one place. Those are the three things that you can notice in this video. Right. So from this video, I'm going to introduce you three basic flight modes. There are more flight modes, but these are the three basic flight modes that we can identify: the stabilize, altitude hold, and position hold. And there are, as I mentioned, there are several other flight modes that you can identify in the modern flight controllers and drones. The stabilize mode could be identified as the basic flight mode, where you need to continuously give inputs to the drone through a radio control. Let's see this video, and this drone is flying in the stabilized mode, and you can see how fast this user is giving control commands to the drone in order to make it stabilize and keep it at one place. So he needs to continuously move the sticks, and if he tries to get his fingers out from the radio controller, even for a moment, the drone will go in a particular direction and crash. You see that again. The point here is this drone is flying in the stabilized mode, which means it's only maintaining its stability or the level of the drone, but you need to control the altitude and its roll and pitch angles, and also the yaw angle. You need to continuously give inputs to the drone using a radio control. That's called the stabilized mode. In the altitude hold mode, we have the privilege of using the stabilized mode plus holding the altitude, which means the drone can hold the altitude or hold or maintain a constant distance from the ground. This video represents the altitude hold mode. So obviously it has the stabilized mode. And apart from that, you can see it's maintaining nearly a constant distance from the ground. And if we try to change the altitude by forcing it, it will automatically come back to the original height. That is when the drone is controlling the altitude. And you can see it's not controlling its horizontal position. That's why the drone controller or the person who is flying this drone has to keep it at one position using his hand. So that's how the drone behave in the altitude mode. Right, and you saw how the drone behaves in the position hold mode in the previous video. You don't need to do anything. You can just take your hands away from the remote controller, and it will maintain a stable position, or it will not go here and there, and it will maintain a constant position while you are not giving inputs to the drone through your radio control. So these are the three basic movements or three basic flight modes that you can identify in the drone. Now we need to understand what sensors are used to achieve or to facilitate the functionalities of these flight modes. Right. So basically, when it comes to stabilize, you don't need to maintain the altitude and maintain the horizontal position when it comes to an outdoor area. Right? We're not talking about the indoor areas at the moment. We are focusing on outdoor areas. So when it comes to stabilize, you need to maintain the balance of the drone, or you need to keep the drone plane in parallel to the ground plane. That's what basically it means. So in order to stabilize the drone, you need to understand the roll and pitch angle of a particular moment, which means if the drone changes its angle, you need to have a sensor to identify that. Let's say the drone is at a hovering at a level position, and let's say there's a heavy wind, and because of that, it changed its roll angle like this. And we need to have a sensor to identify that change in roll angle and to correct that. So the sensor that we used to achieve that functionality is the inertial measurement unit. This is a must when it comes to drone, and in every drone you can see identify an inertial measurement unit if you dismantle the drone or if you dismantle the flight controller. So this is a must. Without an inertial measurement unit, you cannot basically fly a multi-rotor drone. Right? Sometimes you might be able to fly a fixed wing drone if it's fully controlled by a radio controller, but when it comes to multi-rotor drone, you need to have an IMU. So what would this IMU do? IMU stands for inertial measurement unit. It basically gives you two types of measurements, and in some IMUs they give you three types of measurements. The first one is the accelerations, and then the angular rates, and in some IMUs it contains a magnetometer which gives you the magnetic intensities in all three axes. Right. So this is an IMU that you can buy. You can find even in local stores. It's a cheap option. And this is an IMU. It's a high-end IMU, which is usually used in industrial type or military grade UAVs. And I got the chance to work with one of these IMUs, and as I remember, the price is about $60,000 just for this IMU. And if you consider this one, you can buy this for around 800 or 900 rupees. So the main difference is the reliability and the noise levels that it generates. Again, as I mentioned, there are two types of IMUs. One comes with 6 degrees of freedom, and another type comes in 9 degrees of freedom. The 6 degrees of freedom type IMUs, you can get accelerometer measurement, which means the accelerations in the linear accelerations in X, Y, and Z axis. And then you can get the angular rate, which is the rotational rate around all three axes. That's in the 6 degrees of freedom IMUs. And in the 9 degrees of freedom IMUs, you can get magnetic intensities in all three axes, in addition to what you get in the 6 degrees of freedom IMUs. Usually the magnetic fields are used to calculate the heading, or it works as a digital compass, right? Because when flying a drone, sometimes you need to identify where it's heading, and sometimes it might be useful when achieving autonomous flying capabilities. And having a magnetometer is not a must, but having the accelerometer and the gyroscope is it's a vital component when it comes to flight control. Right. So later I'll explain how the drone achieves. It calculates the roll and pitch angle using these accelerometer readings and gyroscope reading, because again, the drone need to understand its roll and pitch angle, not its linear acceleration or the rotational rate. And I'll explain why the drone uses two types of sensors, because basically even if it's a single IMU, inside that there are two types of sensors. So I'll explain why it uses two types of sensors instead of using a single sensor to calculate the roll, pitch, and yaw angles. It's again, in conclusion, this is a must when it comes to a multi-rotor drone. Because of that reason, in some high-end flight controllers and drones, you can identify 2 or 3 IMUs. The reason is that it doesn't matter how big your drone is, this tiny device, if this tiny device fails, then you are in trouble. Even that's a 100-kilo drone, then it will surely crash if this IMU go through some problems or if it malfunctions. So the flight controller or the drone system need to make sure that your IMU is working at a healthy level when the drone flies. So in some high-end or expensive systems, you can identify 2 or 3 IMUs. Just in case one stops working, the flight controller automatically switches to the other IMU. Or there are some complex systems, which I will explain later, how these complex systems achieve redundant systems using several number of similar types of sensors. So usually in this system, you can identify 3 accelerometers, 3 gyroscope, 3 magnetometers, means 3 IMUs with 9 degrees of freedom, and 2 barometers. Barometer, I will explain that in the next slide. Right. So the idea you have to get is IMU is the most critical part in the drone control system, and if that fails, drone will surely crash. Then the barometer. If you remember from the first slide, we talked about 3 flight modes: stabilize, altitude hold, and then the position hold. IMU is critical for all 3 flight modes, but it's mostly used in the stabilize mode. But even in altitude hold mode and the position hold mode, you can see the stabilized mode working, because in the altitude hold mode means stabilized mode plus altitude hold. In the position hold, we can see stabilized mode plus altitude hold mode plus position hold mode. Right? So what we get from a barometer or a pressure sensor is the atmospheric pressure at that moment. We all know the atmospheric pressure decreases when we go high in the sky. So this sensor uses that principle to calculate the relative height that we are in at a particular moment. So using this sensor, the drone can get an idea about the altitude that it flies. So if we can know the altitude, then we can implement a function to hold a constant altitude. Right? So that's how altitude hold function usually works. But there are some downsides of using these pressure sensors. Because if you notice the altitude hold mode in the previous video, or if you get the chance to practically test the altitude hold mode for drone, you can see that it's not holding exactly the same altitude. It fluctuates around, I would say, 20 centimeters, or sometimes it goes around half a meter. The reason is when we calculate the pressure, when we calculate the altitude from these pressure measurements, it has a very, very low resolution, which means we cannot get the exact altitude using this pressure sensor. So that's one of the downside. And then the low update rate. What do you mean by the low update rate? Usually inside the drone, we define a method which helps to maintain the stability as the control system of the drone. This control system has to run at a really high rate. Sometimes it runs at around 500 Hertz. It helps to maintain the stability. In some high-end drones, the control loop runs at 2000 Hertz. So in order to facilitate this control loop, all types of sensors has to give measurements to a matching rate for that control loop, or it has to be tally with the update rate of this control loop. But the problem is when it comes to this pressure sensor, the maximum rate that you can usually get from a standard sensor like this is 100 Hz. So it's not enough at all. So we need a method, a special method, which I'm going to explain at the end of this session, which is used to overcome or compensate this delay and facilitate the high rate control loop and to maintain the altitude of the particular system. So that's the second advantage, the low update rate. And the third advantage is the readings change with the wind speed and temperature. We know from the Bernoulli theorem, when the wind flows, the pressure goes down, which means even we are at a constant height, if there's a wind, the pressure reading goes down, which means with the wind, the drone identifies it's flying at a low altitude rather than flying at the altitude that we commanded, which means when there's a wind, the drone usually go upwards or downwards. But in this case, since the pressure is going downwards, the drone goes downwards. Right, so that's one of the disadvantages. And then even you are flying at the same altitude with the temperature, atmospheric temperature, this altitude reading that the pressure sensor gives changes. So in that case as well, the drone tries to change its altitude. So overall, what will happen if we use this kind of a pressure sensor, the drone will not hold a very constant altitude position, and it will try to fluctuate with a, I would say, at a range of 0.5 meters. But it doesn't matter when it goes higher or when the drone is flying above 20 meters. This kind of a fluctuation is totally acceptable compared to the relatively higher altitude that it flies. But this becomes a problem when we fly at really low altitude, so when we fly closer to the ground. So we'll see again in the next few slides. In low altitudes, there's another system that drones use to identify the distance to the ground. In the proximity sensors, usually there are two main purposes where drone use these proximity sensors, and I hope you all are aware of these three types: ultrasonic, sharp IR, and time of flight sensors. And each sensor has its own advantages and disadvantages. So you need to select the suitable sensor based on your scenario. And the two cases that the drone uses these types of proximity sensors are to hold the altitude at low distances with the ground, or when it flies close to the ground, and then for obstacle avoidance. So we'll talk about the altitude hold again. As I mentioned, when it comes to low altitude or the drone, if you fly the drone close to the ground, flying with the pressure sensor is not reliable because due to the fluctuation that I explained, the drone may lead to crashes or it will collide with the obstacles in the ground. So you need to make sure that the fluctuation is minimum, and you need a precise height measurement or a precise measurements retrieved from the sensor when it compares to the position of the drone and the distance the drone maintains between when it compares to the ground. So in a drone system, we can identify, usually if you turn a drone downside and try to identify the types of sensors that it has. Mainly, if that drone has the altitude hold functionality, you can identify this type of sensor, which is an ultrasonic sensor. So in an ultrasonic sensor, the accuracy is much more higher than the accuracy that you get from a pressure sensor. In that case, you can fly your drone with a minimum fluctuation in the altitude mode. Basically, when it comes to low altitude, let's say the range of your ultrasonic sensor is about 5 meters. So when the drone comes below 5 meters, it will automatically activate the ultrasonic sensor and measures the distance to the ground, and that will eventually help you to maintain constant distance with minimum fluctuation. When you go beyond 5 meters, then the drone cannot use the ultrasonic sensor because it's considered as an out of range measurement. In that case, it automatically switches to the pressure sensor and use the pressure measurements to the altitude hold function. Then the most common sensor that you already know, the GPS sensor. And this GPS sensor is used to hold the position of the drone at a particular place, or basically supports to run the position hold mode. And if I summarize the things that we have discussed up to now, in stabilized mode, the drone uses only the IMU, and in the altitude hold mode, apart from the IMU, the drone uses barometric sensor and ultrasonic sensor if that's available on board. And in the position hold mode, the drone uses IMU, pressure sensor, or the ultrasonic sensor, and then the GPS sensor. The reason is, by using a GPS sensor, you can identify your position in outdoors in the horizontal plane, right? So you measure the altitude in the vertical plane, and the GPS coordinates gives you the position in the horizontal plane. So if you can exactly identify your position in the horizontal plane, then you can maintain that position. Because if the drone tries to move away from that initial position, then the GPS sensor indicates that you're moving this way. Then the drone control system tries to correct that, and it will eventually take the drone to its original position. And methodology that is being used inside the GPS is called triangulation, which uses several satellite signals and then calculate the position in terms of latitude and longitude. And if we talk about the disadvantages of this GPS sensor, the first one and the most concerned one is the low update rate. Usually we can get around 10 Hertz, even if we use a high-end GPS sensor, but usually we can expect a rate around 5 Hertz. So when compared to the high loop rate of the drone's control system, this rate is not even close to achieve the position hold mode. So that's one of the disadvantages. And again, I'll explain at the end of this session how drone overcomes these problems, which means these low update rates, and achieve its flight modes when it comes to altitude hold and position hold. And then usually accuracy is about 2.5 meters in open areas, which means I'll go to the next one as well. Low accuracy in urban areas. If you know a scenario called multipath propagation, when you are in an urban area, you can see there are larger and taller buildings. And since this GPS sensor depends on the satellite signals that it gets, usually when there are buildings, the building surfaces reflect these satellite signals, which acts as a noise for these GPS signals. So if you are in an urban area and if you are traveling among buildings, then your GPS accuracy becomes really low. So you cannot rely on these GPS sensors in urban areas when you are flying amidst building at low altitudes. And even you are at an open area where you cannot find any kind of a tall trees or any kind of obstacle, the accuracy is around 2.5 meters, which means if you solely use this GPS sensor to hold the position of the drone, it will move in an area with a radius of 2.5 meters. But when it comes to actual system, you cannot experience that kind of a movement because it usually hold the position at the same place. But if you use this GPS sensor without using other types of sensors to compensate this low rate and the error, then you cannot experience that kind of a solid position hold. And the last one, you cannot use this GPS sensor for indoor applications because the GPS signals are really low, intensity is really low inside buildings, and also you can experience multipath propagation. So this is a screenshot from that I captured from my WhatsApp. Because usually in your mobile phones you have a GPS sensor. In that, if you try to track your location, it gives this message, accurate to 9 meters, which means even this particular app shows the exact location. It can be vary within a range of 9 meters. But let's say usually a mobile phone has some really complex algorithms to calculate your exact position using various types of sensors. But let's say when it comes to drone, if it has an accuracy about 9 meters, then it's not acceptable. In that case, if that's acceptable, then your drone starts moving in a circle with a radius of 9 meters, which is not acceptable at all. And there's another type of GPS called RTK GPS. If you use RTK GPS, you can get an accuracy of usually less than 1 centimeter. But the downside is if you use RTK GPS, apart from the sensor that you mount on the drone, you need to have this type of a RTK GPS receiver, which is the ground station. And these are really expensive equipment used for some high precision applications. But if you need to solely depend on the sensor that you mount on the drone, then you cannot use RTK GPS because you need to use the ground station like this in that case. Right. So up to now we talked about IMU, the pressure sensor, usage of ultrasonic sensors, and then how the drone utilizes the measurements that it gets from the GPS. Then this is a quite novel sensor for most of the people in the industry. I mentioned in the last slide that we cannot use the GPS sensor to hold the position inside buildings. But we need to have another type of method to maintain a constant position at indoor environments. So let's see how this drone flies. So this is an indoor environment. And the user is not giving any kind of a control input. But as you can see, the drone is holding a relatively stable and a constant position. Let's play that again. So you can clearly see that it's not using any type of a GPS sensor because GPS signals are really inaccurate in indoor environments. What this drone does is it uses a sensor called optical flow sensor. So these are two types of optical flow sensors. This optical flow sensor, and here the one with the lens is an optical flow sensor. The optical flow sensor is somewhat similar to a camera because it has a lens and it can capture the colors from the area that it sees. And as you know, usually in a camera, you can identify a grid, which is called pixels. And in optical flow sensor, what it does is it tries to identify the image, which is exactly beneath the drone, and try to lock that image. The drone tries to move in one direction, then the optical flow sensor automatically identifies the change when compared to the original image, and then it calculates the error. Let's say it's hovering at a particular position, and the drone goes to the left side from 0.2 meters. And then this optical flow sensor has the ability to calculate the direction and the distance that it moved, and then command the control system to correct that error. Basically, if you try to identify this optical flow sensor in a drone where it offers indoor position hold mode, you can identify this small camera at the bottom of the drone. and that's how we achieve position hold at indoor environments. And in outdoor environments, in low altitudes, most of the drones use optical flow sensor and the ultrasonic sensor. And when it goes to high altitudes, it switches to GPS and pressure sensor to achieve the position hold mode. Right. So this is a new concept, sensor fusion. And if you remember, I stated some disadvantages of using pressure sensor, which has a relatively low update rate, which is about 100 Hertz, and then the GPS sensor just about 5 Hertz. So we need to find a method to compensate that error and to achieve a high measurement rate to feed the control loop, which means we need to find a method. Let's say we get the GPS sensor, and we need to find a method to upscale the sampling rate from 5 Hertz to at least, let's say, 500 Hertz. So we use a method called sensor fusion, where we use several types of sensors and we combine them together to identify a particular measurement or to calculate a particular parameter. Right. So let's see what we can simply do with this sensor fusion. So this is the answer for the first thing that I mentioned, why we use two types of sensors inside the IMU, the gyroscope and the accelerometer, because we can use each of these sensors individually to calculate the roll and pitch angle. But the problem is, in each sensor, there are some downsides, which are usually the accelerometer is quite sensitive for vibrations, while the gyroscope it usually has some drifts called random walk. So in order to overcome both these disadvantages, we combine both these sensors in order to calculate roll and pitch. So there are some complex algorithms that we use to fuse both these measurement types in order to calculate roll and pitch angle. But the advantage is then we can overcome the downsides of each types of sensor and achieve a higher rate. And then let's say we need to compensate the low rate and the low accuracy of the GPS sensor. There we fuse the accelerometer readings and the GPS sensor together in order to achieve a higher rate. Because usually the IMU facilitates for higher update rates, and that will help you to compensate the lower rate of this GPS sensor. Because until the GPS sensor gets updated, we use the accelerometer or the linear acceleration to calculate the distance that the drone moved in a particular direction. And once we get an update from the GPS, we correct the predicted measurements that we calculated using the accelerometer. And as I mentioned, in redundant systems where we use 2 or 3 types of sensors to make sure that the drone does not crash once a single sensor fails, there we use a sensor fusion method to make sure that it flies even one sensor fails. And then increase the stability of the system and compensate drift. And those are the disadvantages of some sensors, specifically when it comes to IMUs. So we can get rid of that if we use these advanced sensor fusion algorithms. Again, sensor fusion means we use 2 or several types of measurements in order to calculate one or several parameters. And there's another application, overcome the limitation of sensors in autonomous cars. In order to clearly understand what's happening inside the drone sensor fusion system, I mentioned this example where we can easily identify how an autonomous car works. Usually an autonomous car uses several types of sensors. Radar. Radar helps to get range measurement. It works similar to a proximity sensor. And then the LiDAR. LiDAR is a rotating laser scanner, which also gives you proximity details, but in a 3D environment. Camera. Then camera. Fusion means combining these measurements together. So if we consider the plus sides and downsides of these 3 sensors in radar, the object detection, the both types shows strong capabilities, but when it comes to camera, it usually consumes a lot of computational power, and sometimes in night times you cannot clearly identify objects using a camera. So that's the downside of the camera. Pedestrian detection, you cannot use a LiDAR to detect pedestrians, radar not at all, because the radar provides only range measurement. Using that, you cannot detect a pedestrian, or you cannot distinguish between an object and a pedestrian. And under several weather conditions, you cannot expect a camera to work, especially in misty conditions, and that sometimes applies to LiDAR, where we can experience some kind of snowfalls, and there the radar works fine. And you can go through the other parameters, and as you can see, each sensor has its own strengths and own weak points. So we need to find a method to overcome the weak points of each sensor and to have a reliable method to achieve these autonomous capabilities. So that's why we use sensor fusion algorithms, which usually combines all these types of data and give you a particular type of information. So a simplest application that you can use sensor fusion is, let's say you need to measure distance for a particular object, and instead of using one ultrasonic sensor, you use one ultrasonic sensor, one time of flight sensor, and then one sharp IR sensor. So what you usually do is you get 3 measurements and get the average value to calculate the distance for that particular object. But if you can implement a sensor fusion model using these 3 sensors, then you can achieve much more accurate value to that distance. So that's one of the simplest application that you can use sensor fusion for. So that's pretty much it about what we plan to discuss today. So in conclusion, I'll go through the things that I explained. In order to achieve a stable flight, you need to have an IMU, which stands for initial measurement unit. And then to have the altitude hold mode, you need to either have a pressure sensor or an ultrasonic sensor or any other distance sensors that helps to measure the distance to the ground. And then you need to have a GPS sensor or an optical flow sensor to activate the position hold mode. And at the end, we discussed how these measurements get fused in order to overcome the issues that are present in individual sensors. Right, so that's all about today's session. And if you have any questions, I'm open to answer.
The presentation was fascinating, sir. I'm sure our participants got a lot of knowledge from it. Yes, let's move on to the Q&A session. I want to invite you again, sir, to answer a few questions submitted regarding the webinar. So the first question is, are there any alternatives for LiDAR in drones? How the altitude of the UAV is calculated, and the sensor used to calculate altitude? What are the other systems that can be used for navigation instead of GPS, best flighting controller, and computers for UAVs?
I think there are 5 or 6 questions in one set. So as I remember, I'll go with the first couple of questions, and then you can repeat the question that you got. So the first question is, I think, as I remember, what are the alternatives for LiDAR? When it comes to LiDAR, we use several types of LiDARs for drones, and we usually use 1D LiDAR to detect the distance to the ground, which is an alternative for the ultrasonic sensor. And sometimes we use the 1D LiDAR to detect obstacles. And there are 2D and 3D LiDARs. Both of them can be used for obstacle detection, but mainly used for mapping purposes. There's a topic called simultaneous localization and mapping, where we use the LiDARs, cameras, or other types of mapping sensors to map the environment and to identify our position. All right. So if your application is altitude hold, using a LiDAR, then you can replace that with an ultrasonic sensor or using a time of flight sensor. But when it comes to mapping, and if you use LiDARs for mapping, you can replace that with cameras, basically with cameras. But there are some downsides as well when we use the cameras for mapping purposes. Right. What was the next question in the same one?
The next question is how the altitude of the UAV is calculated.
Right. So as I mentioned, the altitude is calculated by a sensor fusion algorithm. Mainly it uses linear acceleration in this direction. That's used in short-term altitude calculation, and it is been fused with the altitude calculated by the pressure sensor. Because usually if you solely use the pressure sensor values, it's not really accurate, and it has a lower resolution, usually around 0.3 to 0.5 meters. So we need to fuse the accelerometer data to get a better resolution at a higher rate. Right. The next question.
What are the other systems that can be used for navigation instead of GPS, best flight controller and computers for UAVs?
Right. So there are two questions. So what are the alternative methods that you can use for navigation instead of GPS?
Yes.
Right. So in order to achieve an autonomous flying capability, so in order to run an autonomous mission, the first thing you need to do is to localize your drone. Localizing means you need to identify the position of the drone. That's why we use the GPS sensor. But if you can use any other method, there's a method called image registration, where we use a camera to identify the position by making identify particular objects at the environment rather than using GPA. So in that case, if you can clearly identify your current position by using some kind of a landmark, then you can achieve autonomous navigation capabilities. Especially there are researchers which are going on to navigate inside forests where you cannot expect GPS signals with good accuracy, and they use stereo cameras because stereo cameras helps you to identify objects as well as it acts as a depth sensor. Because while detecting the particular types of objects, you can detect the distance as well. So in that case, since you have an idea about your position, you can achieve autonomous navigation. And even if you use a LiDAR, and there are some applications where they use LiDARs to achieve autonomous navigation inside underground mines, and that's an alternative as well. And for the last question, what are the best options? I cannot say for sure because there are several models, high-end models in the market, and in most of the industrial and military grade UAVs, they are not using off-the-shelf flight controllers. The companies are implementing their own flight controllers. The reason is, if you try to enter to the industrial grade UAV market or to the military grade UAVs, there are set of standards that you need to satisfy. So you need to make sure that you have the control over everything which is happening inside the flight control. So in that case, they are not using off-the-shelf controllers. They implement their own by integrating these types of sensors and implementing their own algorithms. Right.
Right, sir. Thank you. The next question is, what is the legal background in Sri Lanka in order to fly a drone? Do we need to have some kind of license from police like that?
Right. I think that's a common type of question. Again, if you go to the YouTube channel of the Bionic Bee Academy, they have done a really good video in collaboration with the Civil Aviation Authority, how you can fly a drone, what are the permissions that you need to obtain in Sri Lanka in a detailed manner. But I'll explain that in short. Roughly, I go through the process that you need to follow when you fly a drone. Firstly, you need to register your drone with the Civil Aviation Authority, and then each time that you fly, you need to obtain permission from the Civil Aviation Authority and the Defense Ministry. And yeah, that's it. So if you're flying near an urban area, or if that's not your own land or home, you need to surely obtain permissions from these two authorities.
Okay, sir. The next question is, can an EMP knock out a UAV military drone? How effective is it? Like, can use drone normally after knockout by an EMP shockwave?
Right. So there are several ways that you can use to jam a drone. This we usually call these as drone jammers. And EMP is one of the extreme methods that you can use to, get rid of this drone problem, or sometimes used as an military tactic. Usually in drone jammers, what we do is we jam several frequencies which is used in radio control system and the GPS systems. In that case, the drone, the algorithms gets confused and the measurements gets inaccurate. So in that case, the drone tries to go back to the home, or it lands based on the safety system that it has. But in an EMP, what happens is if you fire an EMP wave towards a drone, it generates electrical signals inside the drone circuit. So if that's strong enough, what will happen is the sensitive components will get burned. So in that case, the drone will suddenly crash by stopping the internal functionalities. But the main point is the EMP should be strong enough, and it's not legal to use an EMPs in most of the regions, especially in Sri Lanka.
Right, sir. The last question is, how can aerodynamics flow controls like separation control be measured in the real-time flight of a UAV?
Can you repeat that again?
How can aerodynamic flow control like separation control be measured in the real-time flight of a UAV?
Right, so that's related to really advanced flights, because usually what we do in multi-rotor UAVs, we are not in commercial UAVs, we are not dynamically or real-time monitoring these types of flow measurements or the things related to shape of the drone. What we usually do is we do the initial analysis. We try to implement a body shape which has a really good airflow and less drag. But in some cases, when it comes to fixed wing flights, right, we have some types of sensors. Especially, we use a pitot tube that is used for measure the relative velocity using the airflow. But there are some methods that are used in advanced flights. That's based on the sensor fusion methods as well, and some machine learning and advanced algorithms which are used to measure the airflow. And I have seen another method where the drone can change its shape, and in that case, based on the wind speed and the altitude that it flies, it analyzes the flow and the aerodynamic shape which is best fit for in that scenario. But to be honest, I'm not an expert in that particular area, because that comes under mechanical aspects of the drone. Because I have expertise on the control systems and the sensor fusion, and basically when it comes to the electronic integrations, I usually work on those kind of systems. I'm not an expert in mechanical aspects.
Thank you, sir. That's all. Then again, thank you for sharing your expertise, sir. Then now we would like to invite our participants to fill out the feedback form given in the chat box. Okay, now we have come to the final part of the webinar. I would like to invite Ms. Imasha to deliver the vote of thanks. Over to you, Ms. Imasha.
Thank you, Pamodya. Good evening, everyone. I'm 𝚂𝚗𝚗𝚘𝚗𝚜, Secretary of the Aeronautical Division of SEDS SLTC. It is a great pleasure to deliver the vote of thanks on this memorable occasion. First of all, I would like to give my hearty vote of thanks to our guest speaker, Mr. Tharindu Suraj Chathuranga, for making an excellent presentation and making this webinar exciting and very meaningful. I would also like to extend our thanks to SLTC administration for approving and supporting this event. Further, a big thanks to the SLTC Executive Committee for guiding us to make this event a success. And I mainly thank our organizing committee for lending their strength together to make this event possible. Finally, I thank our wonderful participants who have turned up in such great numbers. Thank you so much for your active participation. Once again, I thank you all for your cordial cooperation. Thank you.
Thank you very much, Masha. You can watch the recording of this webinar from the SLTC YouTube page. We have now reached the end of our today's event. Thank you again, sir, for the sharing your knowledge with us and taking your valuable time. And also, once again, on behalf of the organizing committee of DRONERA Chapter 2, I would like to thank you all for your support. Finally, everyone, for your enthusiasts, participations, and thank you. Good evening and stay safe.